So good morning.
Good morning, sir.
And welcome.
Thank you, sir.
So this is a continuation of our discussion, Mass 206, after Algebra 2. So today we are going to talk about cosets and Lagrange's theorem. So I'm going to introduce this cosets is a partitioning of the group in terms of classes with respect to a particular subgroup. But to introduce the concept of coset, we have to start by looking at an equivalence relation that can be defined in a group. So I will define congruence modulo relation. Congruence modulo relation. So you take a subgroup, be a subgroup of a group G, and choose two elements A, B in the group. Then the element A is said to be congruent to, so this is the notion we are defining, congruent, said to be congruent to the element B modulo the subgroup H. This is written as A is congruent to B modulo H. If A, B inverse is an element of H. So you define an equivalence relation for elements of the group in this way. So two elements of the group G are congruent. The first element A is congruent to B if the A times B inverse is in H. So the congruence modulo is with respect to the subgroup. If you change the choice of the subgroup, the element may no longer be congruent. For example, let me give you an example here. You remember, if you consider this subgroup H, say 3Z, that is the subgroup of all multiples of 3 in the group of integers. Okay? In the group of integers, integer under addition. And here you have to take note of the fact that we are donating operation multiplicatively. So that operation in between A and B here, or A, B inverse, it may be addition. So it can be A plus B inverse, and in the additive notation, B inverse is minus.
Yes.
So if you look at this now, you see that in the subgroup, if I take two elements, for example, in the group of integers Z, under, so this is my group G, the group of integers under what? Addition. You can now see that the number 7, the integer 7 is congruent to what? To 1. Modulo the subgroup. Modulo the subgroup. Our subgroup is 3Z. That is multiples of 3. But how do we know that 7 is congruent to 1 modulo the subgroup? is because if we operate A with B inverse, so A is your 7, and then if you take B inverse, it will be minus 1.
Okay.
So here, A, so since 7 plus the inverse of B minus 7, because in this group addition is the binary operation, so inverses will be negative of the number. So what you have here is 6, and 6 is an element inside 3z, because 3z consists of all multiples of 3. So that is what we mean by congruence modulo relation. You take two elements and you take one with the inverse of the other. Like 7 is not congruent to 2. This is because what? 7 plus minus 2. You can write 7 minus 2. It doesn't matter. Is equal to what? 5. And 5 is not a multiple of 3. So this will not be in the subgroup H, 3z. So this is actually what this relation is, congruence modulo relation. So if you take any subgroup of a group and you try to, you can define with respect to that subgroup a congruence modulo relation in this way. Now immediately we can check, because why do we require defining a relation on a group? It's actually to partition the group into equivalent classes. So immediately we now prove that the relation is an equivalence relation. So the relation, so if H is a subgroup of a group G, and A, B are two elements of the group, then the relation, if you take it to be tilde, defined on G, defined by so A is related to B if and only if A is congruent to B modulo H. So you say two elements are related, they are congruent. That is, if A is congruent to B, then A is related to B. And then every definition they said is biconditional, actually. So even if I say they are related if A is congruent to B modulo H, you understand if and only if.
Yes.
So this is it. So we prove this. So what do you mean by equivalence relation? We need to show that this relation is an equivalence relation. What does that mean? You say a relation, oh no, I think I have not finished. The relation defined by this, then the relation defined by this rule is an equivalence relation. It's an equivalence relation. Is that okay? Yes. So that is what we need to show. We need to show that the relation is an equivalence relation. We can prove this result, this lemma. So to show that the given relation is an equivalence relation, we have to show that it is reflexive, symmetric, and transitive. Yeah. So for the relation tilde to be an equivalence relation, tilde as given in the statement of the lemma, to be an equivalence relation, it must be, number one, reflexive. Reflexive means every element must relate to itself in the group. Symmetric. That means if A is related to B, then B must also relate to A. And what? Transitive. Transitive means if A is related to B and B is related to C, then A must relate to C directly. So that is a kind of that is what transitivity of a relation means. So now for the reflexivity, so number one, we check that the relation is reflexive. So 3 things I must to do. Now since for all A, if you take any A in G, A minus A, A with A inverse, this is identity. A with A inverse is identity, but identity is always in the subgroup. So it follows by the definition of our congruence modulo that A is congruent to what? To A. Modulo the subgroup, so that A is related to A and tilde is reflexive. Do you understand this? Okay? A is related to A because A is related to A because it is congruent to itself. Why do we conclude that it is congruent to itself? Because if you multiply A with the inverse of A, you get identity which is inside the subgroup. Because that is how we define this relation of congruence modulo. We say if A times B inverse is in H, then A is congruent to B. Are you following? So that is it. So this proves that the relation is an equivalence, is a reflexive relation. To see that the relation is symmetric, we assume, so suppose A is related to B in what? A modulo. That is, suppose A is related to B for some AB in the group. So suppose 2 elements are related to each other, one A is related to B, and then we now want to show that B is related to A because we want to check symmetry, that the relation is symmetric. Are you following?
Yes.
You did this in your Maths 205 class, so I'm very sure you can still remember these ones when you talked about relations, partial order, reflexive, properties of relations, symmetry, and so on. So if you call a relation symmetric, then you are saying that whenever A is related to B, then B will also relate to A. Okay, so it's symmetric. So, but then by our very definition of what this relation is, if you say A is related to B, then it means A is congruent to B modulo H. Are you following? And then, by the very definition in the statement of the lemma, it means we are saying A is congruent to B modulo H. And so, when you say A is congruent to B modulo H, by the definition of this congruence modulo, it means A times B inverse is in what? It's in H. That is what we have. We now have that. And so AB inverse is in H. But then, you remember H is a subgroup.
Yes.
The subgroup is also closed under taking inverse. So if you take this is an element inside H. So if you take the inverse of this particular element, it will still be in H. Now since H is closed, is a subgroup, the inverse of this element, the inverse of this particular element which we found to be in H is also in H. In H. That is, if you take AB inverse of that, this will be equal to what? So by one of our basic lemmas from the first lecture, you remember, you take inverse by reversing the product. So this will be B inverse times A inverse. Is that okay? And this will be what? B inverse is B times A inverse,
inverse.
and the conclusion is that this must be in H. This is what we say. The inverse of this particular element must be in H. Are you following?
Yes, sir.
So this is in H.
So when you take an inverse, the order of the element changes.
Yeah, if you take inverse of the product, it's the product of inverses in a reverse order.
Okay.
You reverse from the last to the
Okay.
first. So that is how inverse is always. This is called socks shoe principle.
Okay.
That is, if you wear your socks
Yeah.
and put the shoe,
Okay.
like you are looking at the operation of wearing.
Okay.
So put on your socks
Yeah.
and put on your shoe.
Yeah.
If you are inverting,
Yeah,
you have to take the last one. The shoe must go first before the socks.
Okay, that is what is
So you
applicable.
do A operation B, and then you take the inverse, then it has to be a reverse order.
Okay.
Yes, so this is it.
Okay, nice.
Okay then. So but then this is already pronouncing to us that what? B is congruent to A modulo H. Because if this element times the inverse of the second element is in H, then the first element is congruent to the second element. So that's what we have here, is that B is congruent to A modulo what? H. And so A is related to, B is what? D is related to A. So we started with A related to B and B related to A. We end up having B is related to A, so that means
Yes.
the relation is symmetry.
Yeah.
Yeah?
Yeah.
So that
I mean,
delta is symmetry. Delta is symmetry. The last property to check for this relation to be an equivalence relation is transitivity. Is that okay? We now check that the relation is transitive. We say, suppose or assume that A is related to that A is related to B and B is related to A. Related to C. We need 3 points here.
okay.
For some A, B, and C in what? In G, in the group, because the relation is defined on the group G. Well, for some, because it's not necessary that all elements are related.
Okay.
Maybe you have some pair, this pair is arbitrarily taken.
Okay.
Well, you have to check for every pair.
Okay.
I think it should be for all. For all. So if you suppose for all A, B, and C, this is happening, that is, you have to check all pairs, triple,
Okay.
where one is related to the second and the second is related to the third.
Okay.
And then once that happens, then you now say
Transitive.
A is related to C, and if you can check that, then the relation is transitive. So this is what we want to show is that A is related to C. Is that okay?
Yes.
Then by the way this relation is defined, then we are saying A is congruent to B modulo what? H. And the B is congruent to C, again modulo H. Okay? But then, by the definition of this, we have what? AB inverse to be in H, and BC inverse to be in what? In H. Now, since H is you have two elements in H, since H is a subgroup, the product of this element will still be in H.
Okay.
Is that okay? Yeah, because H is closed under multiplication. So again, since H, since H is a subgroup of what? Subgroup of G.
Of G.
So we have that H is closed under multiplication. So it means if I pick that element AB inverse multiply with the B inverse times T, No, B times C inverse, the second element over there. You have A, B inverse, and B, C inverse. And this, you can simplify by associativity. This is A, B inverse, B, C inverse, but this is what? A identity, E being the identity of the group. And that is A, C inverse. This must be in H by the closure property. And if this is in H, then it means A is congruent to C, modulo H. So therefore it means A is congruent to C, modulo the subgroup. And so A is tilde related to C, so that what? The relation tilde is transitive. So we have a transitive relation. So a relation is that is now, we showed that the relation is reflexive, it's symmetric, and it's transitive. That means this relation is an equivalence relation. And that is what we require for a relation to be an equivalence relation. So hence, tilde is an equivalence relation. Equivalence relation on what? On the group G. So we have proved that it is an equivalence relation. Now the question is, so what do we do with it? So if you prove that something is an equivalence relation, you just define a relation. So what is the advantage of having an equivalence relation in a set?
You say to partition the group.
To partition the group into equivalent classes. Yeah, into classes. That is what an equivalence relation will do. So imagine you have your group here, G. This particular relation will now partition the group into classes. Into as many classes. And where elements will be in the same part if they are related to each other. So all elements related to each other are in one group. All elements related to each other will be in one group. So it's like the classes. Yeah. Like become, assuming the whole university is or the whole department is actually is a group. And then you say
no, the university
two students.
Then the
like the whole university is a group, and then you now say two students of the university are related if they are in the same department. So you see, a student can be in two different departments in the university like this. And so therefore, this is an equivalence relation. So it partitions the entire set of the students of the university into classes. These classes are now departments. So this will be a department, another department, and so on. That's the advantage of having an equivalence relation. An equivalence relation are well behaved in a way that what I mentioned, that no single element will be present here and also present there. Yeah, will be found in two different classes. But then what is a class under this? Yeah, because what we mean is this entire group now is partitioned into this classes. So it is like divided by the relation. So the relation will divide it into classes.
The relation is dividing the group now.
Into classes. Like you are dealing with a set of students of the university. And maybe your interest is to know the name of the head of department, every department. So if you ask a particular student of one department and he has given you the information, you don't need to ask the other students. So if you want to now learn something about this class, you only need to contact one member of the class. So you move to the other class to get a new information. Because if you still ask a 100-level student of that department, and you still ask another 300-level student of the same department, it will give you the same information, the same name of the same person as the head of department. So you have to move out. That is the advantage of having an equivalence relation in a group. And we now want to understand the nature of the group. then this relation will do the job for us, will reduce the work for us by partitioning the group into classes. And you now see if you have 1,000 elements in the group, and now you have 1, 2, 3, 4, 5, 6 classes. So you have just reduced 1,000 into 6 immediately by just one equivalence relation. So that if you pick one element from here, that element will be the representative of that class. And whatever information you want to know about this group of elements, the particular element you pick will provide you with all the elements. So like if I want to get an information of which timetable, what is the timetable for a particular class, I only need to contact the class rep. And the class rep will give me the information. So if I have the information from the class rep, I don't need to contact a different person in that class, in that same class. So this is the advantage of having an equivalence relation. Tend to partition the class. But we need to know how is an equivalence relation under this relation looking like. So that is the next thing we now look at. Let's say, so let A, okay, sorry, one minute. So let A, let A be an element in the group G. Then, since we know already this delta is an equivalence relation, then the class of A, so that means I'm assuming A is here. And this is the class of A. So then the class of A, the equivalence class of A under the relation delta is this one. You can write it as A bar. There are a number of notations. One can write it like this. You know,
Okay, I think
like
the more particular is that of the one.
this one. That is what you want. So let me just write it that way. So it's the set of all elements in here that are related to A. So all B in the group such that A is related to B. Or you can say B is related to A because this relation is symmetric. Whenever B relates to A will relate to A. It doesn't change anything. So this is the set actually. But then you can write it because you have a definition for your relation. You can say B in G such that A is congruent to B modulo H. That is what is meant to be related to. And this would be the set of all B in G such that, what is this now? A, B inverse is in H. That is what is meant to be congruent to that. So, and then we can now still have, so you can still write it as the set of all B in G such that an element, you say this product is in H. So that means that product AB inverse is equal to some element H where H is in H. Yeah, it's some element in H. Is that okay?
Yeah.
Write it like this.
Since it's
Or you
closed.
can say it's equal to H in H.
That means it's closed. Closure.
Uh,
A, B inverse in equals to
yeah.
A.
No. This is not closure actually because A and B may not even be element of H.
Okay.
So what you are saying when you multiply A with B inverse, this B inverse is always available in the group.
Okay.
And if you do this product, you always end up with an element inside H.
Okay.
And so you are now saying this is B in G such that, let me just do something here. I think it's better you pronounce this as the set of all element B in G
For all.
such that B is related to. I think if I write it like this, there is no problem. In fact, I made this remark because the relation is symmetric.
The symmetry.
Well, there is a reason why I should write it like this because I want to get at the end of the day B in terms of A. So it doesn't change anything. You will see why I have to do this. B is congruent to A. And whenever B is congruent to A, it will still be, A is still also congruent to B. So better written as, so when you write like this, it means you are saying A, B inverse is in H. I hope it's okay. So it's not a very confusing correction here. It's not even a correction because what I wrote before is still correct, but because of what I want to arrive at. And so here you say B is equal to what? You can do left cancellation, or right cancellation, sorry, right cancellation. Okay, you multiply here with A and multiply here with A, then you have B, A inverse times A. That will cancel A. So you have H times A, where H is an element of H, the subgroup. So that is the very reason why, because I want to write B in terms of A, not in terms of A inverse. And that will be equal to, so this particular B is just HA. Yeah. So which means the B, those B that I'm looking for in G are the B that are written as H times A, where H is an element of H. Are you following? So if you are looking for the congruence class of A, this congruent class of A, that is the set of all elements related to A under our relation, congruence modulo. We just look for all elements inside the group that are multiple of element of H. A multiple of element of H. Element that can be written as H times A, where H is in H. But you know this set you can write it as HA. HA. Yeah, HA. So it has a name, and this is what we call the right cosets of H generated by A. So it's like you have your H, and then all element of H you multiply from the right by this particular element A. And that is the generating element. So we have a definition now. Say, so let H be a subgroup of G, be a subgroup of G, of a group G. And take an element in G. Then the right coset of H, of A, sorry, of H in G generated by, it is the element A that is now generating the coset, generated by the element A is the equivalence class of A under the relation of congruence modulo. Yeah, so it is the equivalence class of A under the relation of congruence modulo. As defined, so let me say as defined above. Because if you change the way you define that particular relation, the coset will change. You know, it's given by HA. This is it. Because that's what we discovered to be the equivalent class. So it is HA. So coset generated by an element, just multiply the element of H by A from the right. And that is what we call coset. Okay? So I will immediately give you a remark over here to say that if the congruence modulo relation is defined it was defined as A is congruent to B modulo H, if and only if A inverse B is in H, then, did you see the difference here between this definition and the one before? The one before, we wrote what? A B inverse.
Yes.
Now I'm writing A inverse
That's B.
B. Did you see it?
Yes.
Okay, you can see the definition now. Huh?
Yes.
I'm changing, I'm writing the inverse. Let me write it like B inverse A. Write it like this. So if I have written the congruence modulo relation in this way, then the equivalent classes, because this will still be an equivalence relation, nothing will change. Then the equivalent class of A in G under this particular relation is now this equivalent class, and it will now be the set of all B in G such that, so B is congruent to A modulo A, B is congruent to A modulo H, and that would be what? A inverse B in H, so which means you are saying this is equal to H in H, some H in H. But you know this one, as we have done it here, this would be the set of all B in G such that B is now equal to AH. It is now a left cancellation of the A inverse. So A will now come from the left of H, where H is in H. And that will be BAH such that H is in H. So you no longer get right coset because A is coming from the left. So what you have is left coset. Hmm? And in this case, the equivalent class, and now the equivalent class AH, which is the set of all AH such that H is in H, is called the left coset now. Left coset of H in G generated by the element A. And a left coset may not necessarily be the same as the right coset, because the group may not necessarily be an abelian group. You know, because left coset, right coset, you are multiplying A from the right of the element of H. And left coset, you are multiplying A from the left of the element of H. So this may not be the same.
So, and that's when they said the left coset is always equal to the right coset, so most of the time it's not always true.
They are not necessarily always true. We are coming to studying a class of subgroup where the left and the right coset are always the same, generated by a particular element. Such class of subgroup is called normal subgroup. Yeah, so and they are the most interesting subgroups that we are looking for, because those are the subgroup that will do a very nice partitioning of the group in a way that the collection of the cosets, the classes, the collection of the equivalent classes will still be a group. Yeah. So we'll still, because it's not necessary that when you do the partitioning, remember I said the group is partitioned into classes like this, by this equivalence relation. So but now if you take this and treat it as a single element,
Yes.
because I say if we pick the class representative, it's enough to represent the class. So you only look at the class representative. So you are looking at this as one element, even though it is a whole class of elements. And you also look at this as one element, and this one element, this one element. So you see, it may be a group of hundreds of elements. But at the end of the day, we have only 5 elements now. So if you treat the classes as element in there, all right, they may not form a group. Yeah, they may not form a group. Are you following? So, but if the group is a normal subgroup, the subgroup originally is a normal subgroup, then this will still form a group. And that is of a particular interest, because that means you can still work with the classes as a group. So it's reducing the entire structure of the group into a very smaller structure, so that you'll be able to now do it. It's like a quotient group. This is what we call quotient group. That's what we are heading to. So we now talk about these cosets. So let us talk more about cosets. So I will just discuss about right coset, but whatever I'm going to say about right coset is also applicable to left coset. So I don't have to keep on repeating myself by stating a result for the right and doing the same for the left. So this is what we are going to do. Now, given the fact that these things are subgroups, maybe you should see immediately that the subgroup itself is one of the cosets. Because if you now ask, what will be this coset generated by the identity element of the group? The coset generated by the identity element. So it immediately follows, okay, that for the identity element, the subgroup, the coset, the right coset of H in G generated by the identity E, the identity E of G is what? It's actually the coset generated by the identity, but you know this one will be HE, such that H is in H. But this is just, HE is always H. This set is H. Nothing is changed, because if you multiply element with identity from the right or left, it's still the same thing. So when one asks you to find cosets of a particular subgroup, he has already presented you with one of the cosets. That is, the subgroup itself is already one of the cosets. And given the fact that these are equivalent classes, if you pick any element from a particular coset, it will still generate the same thing. Yeah, before I prove the next result, let me just give you an example. But this time around, I'm going to take, so you have to recall what the symmetry group is. Let me say, so we will take G to be the group S3. This S3 is the symmetry group with this element, 1. 1 being the identity permutation. So we have 3 objects. 1 is mapped to 1, 2 is mapped to 2, and 3 is mapped to 3. This is the linear notation or cycle notation for the permutation. So, and if we write this, it means 1 is mapped to itself. In the cycle notation, every element is mapped to the next element. It is a successor. The last element in the cycle is mapped to the first element. Like 1, 2 here. So 1 is mapped to 2. And 2 is mapped back to 1. So it's a cycle. And then since 3 is missing in the cycle, it is fixed because it's a permutation. So I'm thinking about 1 is mapped to 2, and 2 is mapped to 3, and 3 is mapped to 1, yeah? And 3 is mapped to itself.
Okay.
So this is what this permutation is. Or you can see it as 1, 2, 3.
Okay.
1 is to 2, 2 to 1, and 3 is to 3.
Okay.
This is the permutation.
Okay.
And then the identity, everything is fixed. 1, 1, 2, 2, 3, 3.
Okay.
Something like that. You have to remember this.
Okay.
And then 1, 3. This time around 1 and 3 are mapped to each other.
Yes.
And 2 is fixed.
Yes.
Then you have 2, 3.
Yes.
1, 2, 3. There will be 3 factorial elements in here. So 6 elements.
Okay.
1, 3, 2. These are all. So take G to be this one. And I claim that this H1, 1, 2 is a subgroup of this. Or it is being a subgroup of S3. I don't know that we have introduced this notation. If H is a subgroup of some group G, then you say H is less than or equal to G. To mean H is a subgroup. So this is a subgroup of S3. Yeah, because of the fact that this is closed and it satisfies the properties of being a group. Okay? It's finite, you know, if a subgroup is finite, a subset is finite, you only need to show closure property to conclude that it is a subgroup.
Okay.
So what are the cosets? The question is find all the left and right cosets. Find all left and what? Right cosets of H in S3 in the symmetry group on N symbols. So let us do this one. You still have time? Still have time?
Just take 35.
Okay. So we are looking for all the left cosets. Yeah, what is it? The left coset is just to pick element from the group and multiply H with that element from the left. So the left coset are by the way we start with the identity. And whenever you multiply with identity, you know identity doesn't change anything. This will still be H itself. And that is what? 1. Yeah, so it's still H. It's 1, 1, 2. That is what we have picked to be H. So, but how about if I generate a coset with 1, 2? That means I should multiply all the element of H by 1, 2 from the left.
Yes.
So this will be what? 1, 2, 1, 1, 2, 1, 2. Is that okay? But you know, you can, so well, just look at me here because maybe you may not remember how to do this multiplication. These are mappings, so we are doing composition.
Okay.
So if you are to look for the image of 1,
Yeah.
because we are writing in the linear notation, so the next point we are writing here will be the image of 1.
Okay.
So we now look for the image of 1 in this product. So we perform this product in this way. 1 is mapped to 2.
Yes.
You pick 2 and come to the next cycle.
Okay.
So since 2 is not there, it is fixed because this is identity. You say 1 is mapped to 2 and 2 is mapped to 2 here.
Okay.
So therefore 2 is the final point you arrive at. So 1 is mapped to 2.
Yeah.
And then you now look for the image of 2 because that should be the next element to write.
Okay.
You say 2 is mapped to 1 and 1 is mapped to 1. So 1, but you don't write no repetition of entry in a cycle. Since 1 is already there, you close the cycle. So that means the last element is coming back to the first element. Are you following?
Yes.
So which means this is it. And if you look at 3, 3 is mapped to 3 here, and 3 is mapped to 3 over here. So 3 is fixed. The fixed element, you don't have to write it. Okay, so that means this is 1. But you can look at it as this is identity already, so it doesn't change anything, you just copy 1, 2 down. Are you following?
Yes.
So, and then here, you have 1 is mapped to 2,
Yes.
and 2 is mapped to 1, which means 1 is to 1. And then 2 to 1, 1 to 2, 2 to 2 again, so you don't need to write it.
Okay.
and 3 is to 3, and 3 is to 3. So this product is still 1. We are still getting H. Why? Yeah, it's expected. Because we pick 1, 2 from the same class. You remember I told you, element coming from the same class will not furnish you with any new information.
Yes, it's same.
Are you following? So if you generate a coset, and you still pick an element of that coset you have generated to generate another one, you will end up just wasting your effort because you are just generating the same class. It's just like you changing the class rep. I just say, I no longer want him to be my class rep, it's him I want. So, but it's still the same class. Changing the class representative doesn't change the class itself. It's still the same class. So here I'm looking at this same class, but 1 is my representative. But this is still the same class because 2 is a member of that class. Now, another lecturer may decide to say, okay, no, it is 1, 2 that I want as my class rep, but it's still the same class. Are you following?
Yes.
So you don't change anything. So if you want to generate a different coset, apart from this one, you have to look outside of that coset. So which means we pick an element of the group from outside of the coset. We have seen 1, 2 is not giving us any information. But 1, 3 is from outside that class. So definitely it will generate a new coset. So I pick 1, 3 is as my representative, and then it will provide me with all other members of the class. So this is what we are going to do. So 1, 3, and then H. Now 1, 3, so you say 1, 3 times identity, and 1, 3 times what? 1, 2. And then, you know, if you multiply with identity, you just get the element back. You don't need to waste time there. But then 1, 3, you can do this one now. 1 is mapped to 3, you say 1 is mapped to 3. You always write 1 and then you look for its image. 1 is mapped to 3, and over here 3 is mapped to 3. If an element is missing, it's mapping to itself. So 1 is mapped to 3, and 3 is mapped to 3. That means 3 is the image of 1. Then you now look for the image of 3. So 3 is mapped to 1, and 1 is mapped to 2. So 2 is the image of.
So that 3 come again because the 3, the image of the 3. You say 1.
You start with 1 and you look for the image of 1. And then you now work like this. 1 is mapped to 3. You pick 3 and come to the next cycle. If it is missing in the cycle, it is fixed. So 3 is mapped to 3. 3 is the last element I arrive at, so it will be the image of 1. And then next element to write here would be the image of 3. So you start with 3 in your product. So 3 is mapped to 1, and 1 is mapped to 2. So 2 is the image of 2, of 3. Are you following? And then, well, if you are clever enough, you can see that you have only 3 cycles, and it is 3 points, and it is a permutation. So the only place 2 can map to is back to 1. So you can just close it without even having to perform it. Are you following? But then if you still want to verify that 2 is surely mapping to 1, you can do 2 to 2 here, and 2 to 1. So therefore 2 is coming back to 1. So this is actually this. Are you following? Now to get a new coset, you have just done it. If you use 1, 3, 2, it will still give you this one back. Why? Because it's a member of that class. So this will still be the coset generated by 1, 3, 2. Are you following? Now, we pick a new element. Like for example, if I take 2, 3, okay, because it's nowhere found in the already generated coset. So we have 2, 3, 2, 3, H. 2, 3, H would be what? 2, 3 times 1, okay? And then we have 2, 3 times 1, 2. And that would be what? Well, over here, I just write 2, 3 because I'm multiplying with identity. So nothing is changing. But now, I'm looking for the image of 1. So 1 is mapped to 1 here. And 1 is mapped to 2, which means 1 is going to 2. 2 to 3, and 3 to 3. And then 3 will close. So this coset is the one also generated by 1, 2, 3. To get a new coset, we do what? We look outside of all these cosets. But do we have anything more outside?
No, I think
all the elements have appeared somewhere. So therefore, these are all the cosets. We have this H as one of the cosets, this one and that one. So you can see that this coset is a partition of the group.
So I want this 1, 3, 2. I think I will accepted it.
1, 3, 2, what?
And the second.
1, 3, 2 is already here.
Okay.
One
Okay.
generated by
Okay.
1, 3. One thing we immediately observe is the entirety of S3 is a union of H, H being the coset generated by identity and 1, 2,
Yeah.
and the coset generated by 1, 3, union the coset generated by 2, 3. Once you unite all these cosets, and that is what I was saying about the partitioning.
Okay.
So, but then you can now see you have subdivide. It was a set of 6 elements before, a group of 6 elements, but you have now reduced it to 3. So, and because you are now seeing this as 1, this as 1, and so on. Okay? Now the right coset. The right coset. The right coset. These ones are. So, again, if you generate with identity, you still get H back. Are you following?
Yeah.
So, which means this H is both left and right cosets. So, there are some cosets that will appear to be both left and right, like this particular one. 1, 2, it is still H. And I don't have to waste time generating with 1, 2 because it's still giving me the same thing. So, I will now use 1, 3 to generate the coset. And then I have 1, 1, 3. I have 1, 2, and 1, 3. And then if you do this product, so this composition will give you what? 1, 3. 1 is mapped to 2, and 2 is mapped to 2 here. So 1 is mapped to 2. And 2 is mapped to 1 over here, and 1 to 3. So this is the 3. This will still be the coset generated by 1, 2, 3. And this is still the one generated by 1, 2, the right coset. And then you can use 2, 3 to generate a coset. This will give us 1, 2, 3, 1, 2, 2, 3. This will be 2, 3. 1 is mapped to 2, and 2 is mapped to 3. So 1 to 3. 3 is to 3, and 3 is back to 2. So 2 here, and then you can close it. But then you have 1, 3, 2. And these are all the cosets. And again, this coset partition.
No, okay, 2, 3. Coset generated by 2, 3.
Yeah, 2, 3.
Yeah,
It's still the coset generated by 1, 3, 2 because 1, 3, 2 is a member here. So it will still generate the same thing for us. So this is still H union H 1, 2. Is that okay? 1, 3 union H 2, 3. But now you can see that the coset generated by 1, 3 is 1, 3. The right coset is 1, 3, 1, 2, 3. And this is not the same as the coset, the left coset generated here. You can see there is the differ. Okay? So one thing you can observe is what? The coset generated by 1, 3, the left coset is not the same as the right coset generated by 1, 3. Yeah. Likewise, the other one generated by 2, 3 is not the same as the right coset generated by 2, 3. So it's not always the case that left and right coset will coincide. Except for the coset H. The one generated by identity is always the same as the subgroup. So it's both left and right. So, but there are subgroups where left and right coset are always the same. Maybe I will do that example. So now consider, so find, let me example again. Find all cosets, both left and right, of K this subgroup 1, 1, 2, 3, 1, 3, 2. So this is a subgroup of what? Of S3. So in S3. Let's say a subgroup in S3. You can check that this thing is a subgroup as an exercise.
Okay.
It's not difficult to see. You can just do a multiplication table and see that everything is happening there.
Okay.
Or you can check using subgroup criteria.
Okay.
It is closed and it's because of the finiteness, closure is enough.
Okay.
So the left coset. So we take one identity, we generate k. No problem.
Yeah.
And you know k is 1, 1, 2, 1, 2, 3, 1, 3, 2. You can also, you take, so I don't have to use this element because they already appear in this coset, they will generate the same thing. So I pick an element from S3 different from these ones,
Yeah.
like 1, 2. And I use 1, 2 to generate. Then I get what? 1, 2, 1, 1, 2, 1, 3, 1, 2, what? 3, 1, 2, 1, 3, 2. You can do the composition now. This is identity, so it is 1, 2 again. 1 is mapped to 2 and 2 to 3, so 1 to 3. 3 is to 3 here and 3 back to 1. This will close and 2 will fix. Okay? 1 is to 2 and 2 to 1, so 1 is fixed. 2 will be mapped, 2 is mapped to 1 and 1 to 3. 3 to come back to. This is the coset. And all the elements of S3 have appeared because we have 6 of them, 3 here and 3 over here. So no more cosets. So we have only 2 cosets here. Okay? How about the right coset? For the right coset, we generate using identity, and it is k still. And k is 1, 1, 2, 3, 1, 3, 2. Is that okay? And then we can use still 1, 2, that same element to generate, and that will give us what? 1, 1, 2. 1, 2, 3.
You say right coset.
1, 2. Is that okay? 1, 3, 2, and 1, 2. Well, something that is very clear here is the fact that we have, you see, this coset must contain 3 elements. And the 3 elements have already appeared inside the first coset. So the remaining 3 elements in S3 must be the ones here. So you have no difficulty seeing that this product will still give 1, 2, 3. But if you do this one, it's going to be 1 to 2, 2, 3. So 2, 3 here. And then this one will give us 1, 3 over here. So you will have no difficulty seeing that this product is going to be this, which is still this. So for this particular subgroup, every left coset is a right coset. And every right coset is also a left coset. Yeah? You can see that the coset generated by 1 is still the left coset generated by 1. The right coset generated by 1. And the left coset generated by 1, 2 is still what? The right coset generated by 1, 2. So this subgroup, so there are subgroup where cosets, left and right coset are always the same. There are subgroup where left and right coset are not the same. This kind of subgroup are called normal subgroups. Those that have the same left and right. There is no distinction between left and right cosets. And these are the nice subgroups, the ones that will play a crucial role in group theory. Okay? Is it time for your lectures?
Yes.
Okay. So I think we can stop here. In the next class, we'll start looking at the properties of this coset, and then we'll state and prove Lagrange's theorem. Thank you very much.
Thank you, sir. Thank you, sir.
So, taking algebra